So, my dear student friends, once again we are continuing about the previous class where we discussed about diffusion through the solids, and one of the examples that we discussed, one of the things that we have discussed, diffusion through the non-porous solids. And in addition to this, sometimes what will happen, diffusion is also going to occur in the crystalline solids. And in the crystalline solids, when you talk about the diffusion through the crystalline solids, and the diffusional flux is going to depend on the what is the nature of the material and what is the crystallinity of the material. These are the two things which are important, and how the diffusion is to explain about how diffusion is going to take place. And this can be the diffusion through the crystalline solids can be explained as interstitiality mechanism and vacancy mechanism, then interstitiality mechanism, then we have crowd ion mechanism, then diffusion along grain boundaries. So, as we are discussing in the last class, we were discussing about the diffusion through the non-porous systems. When you talk about the diffusion through the non-porous systems, when you talk about the polymeric matrices, then as I have told you about, there will be absorption, there will be diffusion, there will be desorption. But when you are talking about a crystalline solids, there will not be any absorption or diffusion or the desorption, and still the movement is going to take place, still the diffusion is going to take place, and this diffusion is going to depend on the what is the crystallinity of the material and what is the nature of the materials. And accordingly, there are 5 sorts of mechanisms that are going to take place: interstitiality mechanism, vacancy mechanism, interstitiality mechanism, and the crowd ion mechanism, and the diffusion along the grain boundaries. As I have told you in the previous class also, nowadays people are talking about instead of polymeric membranes, one can use the zeolite membranes. When you are going to use the zeolite membranes are sodium aluminum silicates, and it doesn't have any absorption, but still the diffusion is going to take place. The question now comes into the picture, why this diffusion is going to take place? That diffusions may be explained by this sort of 5 mechanisms. In the case of interstitiality mechanism, and there will be some vacant, this is the places where we have a interstitial sites, and we have one interstitial site will be there, and when this interstitial site is there, now this is going to be moving to this place, or maybe this is moving to this place. So this interstitial sites are there within the matrix, and because of this interstitial sites, the molecules which is there at the interstitial at one of the interstitial site may be moving from one location to the other location, and because of this the diffusion is going to take place. And the second mechanism, what we are going to call it as vacancy mechanism. In the case of vacancy mechanism, maybe one of the interstitial site is vacant. Maybe let's say this interstitial site is vacant. When you say this interstitial site is vacant, now what will happen? So this is the vacancy place. Now this molecule which is there at one interstitial site will be moving to this location, and when it is moving to this location, again this place is vacant, and now this molecule is coming here. Maybe when it is coming here, so this molecule now is coming into this. Maybe now this molecule is going to coming into this thing. So what we want to say, if there is one interstitial site is vacant, the molecules are moving from one interstitial site to the vacant site, and etc., etc. Ultimately the diffusion is going to take place. This is what we call it as a vacancy mechanism. In the case of interstitiality mechanism, now what we have one interstitial site occupied by the bigger molecule. Maybe this is the one interstitial site which is occupied by the bigger molecule, and when you say this is the bigger molecule which is so big, what it will do, it will push the other molecules to the lattice sites. Like we have a very bulky molecule here. This bulky molecule will pushes this molecule, so it will occupy this. When it occupies this thing, and maybe this molecule comes here. So this bigger molecule which is present at the interstitial site will pushes the other molecules. Ultimately what will happen? So these molecules are going to have a permanent movement. When these molecules are moving permanently, that means that is what we call it as a diffusion. So in the case of interstitiality mechanism, there is a big molecule which is present at one of the interstitial site. When it is present at the interstitial site, it will pushes the other molecules. Ultimately the molecule is going to come out. Then in the case of crowd ion mechanism, what will happen? So there will be any extra atom. These are the interstitial site, and there may be any extra atom in the lattice site. So when an extra atom is there in the lattice site, so this, that is what we call it the crowd. We have only fixed number of sites, but we have extra atom is there at one of the location. So when it is the extra, it is there, that is what we call it the crowd. This is what we call it the crowd. So crowd ion mechanism, one extra atom will be there. When an extra atom is there, so this atom will pushes the other molecule, other atoms, and ultimately there will be a diffusion is going to take place. In the case of diffusion along the grain boundaries, we have a single crystals, we have a multi crystals. So when you talk about the multi crystals, when you talk about this multi crystals, along the surface there will be some sort of a diffusion is going to take place. That is what we call it as the diffusion along the grain boundaries. So when we are talking about the zeolites, when we are talking about the zeolite membranes for the applications of gas separation, maybe applications into the liquid separations, people are not understanding how the diffusion is going to take place. One of the things that we can talk about diffusion along the grain boundaries. So we have a single crystals. When you talk about the diffusion through the single crystals, is a very, very small compared to the diffusion through the multi crystals, because there will be some sort of a grain boundaries are there, and along that grain boundaries the mass transfer is going to take place. So that is what the one can explain about that. Then the next topic is we are going to discuss about diffusion through the porous media. And as we discussed already, we have discussed about three things. One is nothing but a very large pores are there. When the large pores are there, a simple the diffusion is going to take place. Like as we discussed already, we have very, very large pore is there. And when it is a large pore, the fluid particle somehow it enters into the large pore and it comes out from the large pore. That is what we call it as the diffusion through the porous solids. And sometimes what will happen, the pores are not so big, and these pore sizes are smaller than the mean free path size. Then as we discussed, we have a Knudsen diffusion. So what we can call it as we can have the bulk diffusion and we have a Knudsen diffusion. And this bulk diffusion is going to be occurs if d by lambda is greater than 20. And this Knudsen diffusion is going to be occurs if d by lambda is less than 0.2. And in between 0.2 to 20, both Knudsen diffusion as well as the bulk diffusion is going to take place. So now the next question comes into the picture, how to handle these sort of situations. Now, and sometimes what will happen, so these are the straight cylindrical pores. Sometimes the pores may not be straight and cylindrical. The pores may be a zigzag pores. And we can have the three sorts of classifications, and one we call it as the interconnected pores. Like if you see, I have a matrix here, I have the pore here, and another pore is there here. Now this pore and this pore is going to be connected. I have maybe a pore like this. So this pore and this pore is going to be connected. Maybe I have the pore here. So this pore and this pore is going to be connected. Maybe I have the pore here, this pore and this pore is going to be connected. Now if you see, these pores are interconnected. It is not a straight pores what we have discussed previously. The pores may not be straight, but however the pores are interconnected, and because of this the diffusional length is going to be increasing. In this case the diffusional length is only of this, but in this case this is not the diffusion length, this is the total diffusion length is going to become like this. So when the diffusional length is going to be increasing, obviously one can expect a more resistance. When you expect a more resistance, the flux will be less. So the pores are classified into the interconnected, and there is another pores what we can say dead end pores. There are pores we call it as a dead end pores. In the case of dead end pores, what we have a matrix is there, we have a pore is there. When we look at from the top, there will be a pore is there, and but inside if you are going to see, there is another pore here. These two pores are connected, but now there is no further path here. This pore is closed here. And this sort of a pores we call it as a dead end pores. Then we call it as another pore, another type of pores, we call it as isolated pores. And when you talk about the isolated pores, if you look at the matrix, and from the top surface if you are going to see, there are no pores, and the bottom surface if you are see, there are no pores, but still inside there is a pore. Inside there is a pore, and this sort of a pores are called as the isolated pores, and these isolated pores are inaccessible to the fluid. Your fluid is here, or your fluid is maybe there, but this fluid is not accessing these pores, and this sort of a pores are going to be called as a isolated pores. Even though we have a pores, but the fluid flow is not going to take place because these pores are not accessible to the fluid flow, not accessible to the flow, and this is what we call it as the isolated pores, and which are inaccessible for the fluid flow. So these are the three types of pores that we are going to come across: interconnected, dead end pores, and isolated pores. Then we are going to call it another thing, we call it as the bidispersed pores. In the case of bidispersed pores, we have a powder and we are making we are compressing the powder. When you compress the powder, we have two types of pores we are going to come across. We call it as a micropores, and we call it as another thing is the macropores. In the case of micropores, I have some particle. The particle will have some porosity, and that is what we call it as the micropores. But now if I have the two particles, this is the one particle, this is another particle, now I am trying to compress these two particles. So when even whatever the way you compress it, there will be a lot of empty space will be there, and such type of pores we call it as the macropores. So a given matrix may have the micropores, may have the macropores, and in the case of a single catalyst particles, we are going to come across a micropores, but when you bunch the catalyst particles, we are going to come across micropores as well as the macropores, and both will participate in the fluid flow. Both will be participating for the mass transfer to take place. So this type of pores we call it as the biodispersed pores, and we are going to define a factor, we call it as the tortuosity factor or tortuosity. And this tortuosity is, if you see, this is the this type of pore, if you are going to see, the diffusion path length is very large compared to the actual path length. And we are going to define a parameter called as the tortuosity, and this tortuosity is defined as what is the actual path length, what is the actual path length, and what will be the path length if it is a straight pore. Actual path length divided by path length if pore is straight pore. If the path length is actual path length that is taking place for the mass transfer to occur, and if the path length is there, if the pore is there, straight pore. So this is the thing what we call it as the tortuosity factor. This is the thing we are going to call it as a tortuosity factor. So when you are talking about diffusion through the pores, there will be several of the complications that we are going to come across. The porosity may be changing, and pore sizes are going to be changing. Maybe this is the one pore that we say maybe having some size, and another pore will not be having the same pore sizes. So we will not have the same pore sizes, and the pores are not a straight pores, the pores are zigzag pores, and all those things makes very complex situations, and the study of material through the porous media is not so simple. It is a very complex problem. Then we cannot calculate the real paths, and we cannot calculate maybe when you are going to see, when you are looking at this surface, maybe we are going to see that there is a pore is there, but this pore will not be permitting any sort of a diffusion to take place. So what I want to tell you, even though there are pores, these pores are not straight pores. These are the zigzag pores. Some of the pores are not interconnected. There are some sort of a dead end pores. When you look at all these things, then the study of permeation through the porous media is so complex, and that is the reason it is not possible separately what is this pore length, what is this pore length. It is not possible to calculate all those things. So we are going to calculate flux based on the cross section area. I think, do you understand or not? What we are talking about, if in the case of simple fluids, we know surface area, what is the surface area. But when you are talking about the porous medias, we have a big matrix is there. The whole matrix doesn't have the pores. The matrix, some pores maybe we are maybe having some pores, some pores may not be, we are not having some pores, and it is not so simple to calculate the fluxes and all those things. I mean, it is not so simple to calculate the area for the flow, individual pore areas we cannot calculate, and if the pores are like this, if it is not a straight and cylindrical pore, and the calculations of the area is going to become much more difficult. That is the reason what we do is we are going to take the gross cross section. And we are estimating the flux based on the gross cross section. And obviously, when you are going to estimate the flux based on the cross section, this flux will be very, very small compared to the actual fluxes. And that is the reason we have a parameter called as the DAB effective. if it is a DAB effective, and this DAB effective is very small compared to the actual DAB values. So this is the DAB effective, and for a given solute system, DAB effective by actual DAB will be a constant. For a given system, the DAB effective by maybe DAB is constant, or maybe one can say DAB by DAB effective will be constant, and this will not changes even if you are going to change the solute. Like for example, if I am going to perform some experiments with a given membrane, I am able to find out what is the value of DAB effective by DAB. This will be a constant. When I am working with some other system, this constant again will be equal to DAB effective by DAB. So what I want to tell you, the DAB effective will be smaller than the actual DAB value. But however, the DAB effective by DAB is equal to constant. And now, as we told, this is the mean free path, and this mean free path is d by lambda is greater than 20. The bulk diffusion is going to take place, which is so simple. Diffusion is normal diffusion, but however, the diffusion is taking place through the pores, and your flux can be estimated as your Na is equal to Na by NB into DAB effective. We don't use the DAB value, we are going to use the DAB effective divided by RT into PT by Z ln of Na by Na plus NB minus Ya2 divided by Na by Na plus NB minus Ya1. That is, if d by lambda is greater than 20, that is diameter of the particle fluid to the mean free path of the particle is greater than 20, simple bulk diffusion is going to take place. And when the bulk diffusion is taking place, this is the expression already we have seen when we are discussing about the diffusion through the fluids. But only the difference what we are going to write, instead of DAB value, we are going to write a DAB effective value. As I have told you, the pores are not straight, the pores are zigzag pores, there are some pores not accessible, there are some pores, isolated pores, and all those things are there. So the actual DAB value will be higher than the DAB effective value, and we are going to use the DAB effective value for the calculations of the fluxes. Then if d by lambda is less than 0.2, this is what I told you, the Knudsen diffusion is going to take place, and where the molecular collisions are not that important. The molecular collision, as we have discussed already, there are two molecules are there, and whenever these two molecules are there, the molecules are randomly moving from one location to the other location. When these two molecules are moving one location to the other location, there will be a collision between the molecules. And the distance traveled by the molecule before collision to occurs, what we said is the mean free path. But in the case of Knudsen diffusion, this mean free path is so high compared to the pore diameter, where the d by lambda is less than 0.2, your bulk diffusion is not going to take place, and that means there will not be any molecular collisions. There will be collision between the molecules and the pore wall. And this is the pore, this is the molecule. Now there will not be any collision between the two molecules. What will happen? So this A may be entering here, it will be traveling like this. So before it reaches to the other molecule of B, there will be a collision with the pore wall, and it is going to take the diversion. And when before reaching to the B molecule, again there will be obstruction by this pore wall, it is going to take the direction change. It takes the direction change. It takes the direction change. Ultimately it comes out. This is what we call it as a Knudsen diffusion, and this Knudsen diffusion is going to happen when the d by lambda is less than 0.2. And there are some expressions for the calculations of the d value and lambda value, and this lambda can be estimated, this mean free path can be estimated as 3.2 mu divided by Pt into RT by 2 pi Gc into m to the power of 0.5. Where mu is the viscosity, or as you know, Pt is the total pressure, T is the temperature, pi value simple constant, Gc is the constant, m is the molecular weight. So if you know the viscosity, If you know the temperature, if you know the pressure, if you know the molecular weight, one can calculate the lambda value. Once if you get the lambda value, we can find out whether the bulk diffusion is taking place, whether the Knudsen diffusion is taking place. If the bulk diffusion is going to take place, we can use the previous equation. If Knudsen diffusion is going to take place, maybe what we have to do, we have to formulate the expression for the calculations of the flux that can be estimated as Na is equal to d into u by 3 RT L PA1 minus PA2, PA1 minus PA2, where UA is a molecular velocity. This molecular velocity is given by the kinetic theory of gases, that is equal to 8 Gc RT by pi into Ma to the power of half. And now once if you substitute UA into Na, this is going to becomes Na is equal to 8 Gc RT divided by pi into Ma to the power of half into d by 3 RTL PA1 minus PA2, and this is known as dKA, where dK is Knudsen diffusion coefficient for component A, into PA1 minus PA2 divided by RTL, where RTL is having its own meanings, where L is nothing but a length of the pore. And here now dKA, Knudsen diffusion coefficient, is given by d by 3 8 Gc RT by pi into Ma to the power of half. And now according to this equation, the diffusion coefficient, Knudsen diffusion coefficient, is is proportional to the T to the power of half, is inversely proportional to the molecular weight to the power of half, molecular weight to the power of half. That means if temperature changes, Knudsen diffusion coefficient changes. If molecular weight changes, Knudsen diffusion coefficient is going to change. So your flux value is going to be changing, and this is the way one can estimate the diffusion coefficients. Suppose when you are going to talk about a binary gas mixers, and these two gas mixers, I have a binary gas mixer A and B. This A and B are at same temperature, but the molecular weight of A is different, the molecular weight of B is different. And once if you say this thing, the flux of A to that of flux of B is equal to MB by MA to the power of half. This is the most important expression that we are going to use for the separation of isotopic mixers. This is the most important expression that we are going to use for the isotopic mixers. Now you look at this problem again. This is the expression that we are going to use to calculate the Knudsen flux when Knudsen diffusion is going to take place. In this expression, only thing is dKA. This dKA is equal to d by 3, where d is the pore diameter, Gc constant, R is the universal gas constant, T is the temperature, Ma is the molecular weight. If partial pressure of the two components are same, PA1 and PA2, PB1 and PB2 are same, only the difference that is going to be there, only the difference is of the molecular weight. Now, if you substitute everything constant, you can write for the flux of component A is inversely proportional to the Ma to the power of half. Flux of component B is inversely proportional to the Mb to the power of half. So Na by Nb is equal to Mb by Ma to the power of half. That means if there is a small variations in the molecular weights, one can find there is a difference in the flux. This is the most important expression used for the separation of isotopic mixtures of pitch blend, where pitch blend is nothing but uranium-238 and uranium-235, and both are having the same vapor pressures. The uranium-238 and uranium-235 is having the same vapor pressures, but for many applications we need to have a uranium-235 isotope, and when you talk about the uranium-235 isotope, to separate from the uranium-238, there is no other mechanism other than the separation by gas separation using porous membranes, where the diffusion is taking place through the Knudsen diffusion. Through the diffusion is taking place, Knudsen diffusion. So now when you talk about your isotopic mixtures of uranium-238 and 235, we have molecular weight of uranium isotope 238, molecular weight is 238, this is 235 to the power of half, and this flux is going to become, the ratios of the fluxes is going to become 1.014. The ratios of the fluxes are going to become 1.014. Even that 1.014 is the most important parameter that is attracted the people to estimate the attracted the people to use the gas separation by a porous membrane where the Knudsen diffusion is taking place for the separation of uranium 238 and 235, and they are going to use the multi stages where more than 300 stages are used for the separation of uranium isotopes. So this is the most important thing, that is what I want to talk to with you. And one more important thing that we can say, if the pores are straight pores, straight away we can say it is a DKA. But as we discussed already, the pores here also, the pores are not straight, and we cannot use the DKA. We are going to use the DKA effective. Do you understand? And if the pores are straight away we can say DKA, Knudsen diffusion coefficient. If the pores are not straight, and we are going to use the fluxes are a little lower than the actual fluxes what we have calculated, so we are going to write a DKA effective. Again here also it is so fortunate, DKA by DKA effective is almost constant, and which is also equal to DAB by DAB effective. DAB effective. So that means for a given solute system, if I can find out the DAB by DA effective, if I am going to get some constant value, that itself DKA by DKE effective. So once if you know this thing, once if you know DKA value, one can find out the DKA effective value and we can calculate the values. So when you talk about the system where we have d by lambda values between 0 to 0.2 to 20, then your flux Na is equal to Na by Na plus Nb, DAB effective, PT, RTZ, ln of Na by Na plus Nb into 1 plus DAB effective divided by DKA effective minus Ya2 whole divided by Na by Na plus Nb 1 plus DAB effective DKA effective close Ya1. So if mole fractions are known, if the diffusion coefficients for the bulk diffusion coefficient for the Knudsen diffusion coefficient, if you know that, one can estimate the flux, and that can be done when we have a d by lambda which is between 0.2 to 20. If it is a d by lambda is greater than 20, as we discussed already, instead of DAB we are going to use the DAB effective and we are going to calculate the flux. And if Knudsen diffusion is going to take place d by lambda which is less than 0.2, instead of DAB effective we are going to use the DKA effective, DKA effective, and we calculate the fluxes. But if the d by lambda is between 0.2 to 20, d by lambda between 0.2 to 20, then both Knudsen diffusion as well as the bulk diffusion are going to be important, and one can use this expression to calculate the flux values. So this is what I want to explain you about the things. Just it will be very clear when you are going to solve a simple problem on this thing, where estimate the Knudsen diffusivity of ethanol within a 100 angstrom unit pore of a catalyst which is at 600 degree Kelvin. We have to estimate the Knudsen diffusivity value of ethylene within a pore of 100 angstrom units, and the temperature is at 600 degree Kelvin. So the temperature is given as 600 Kelvin. RP, the pore radius, is given as 100 angstrom units, that is nothing but 10 power minus 6 centimeters, and the molecular weight is given as 28, the R value 82.1 centimeter cube of atmosphere kg/mole. This is the value of R value, and you know your Knudsen diffusion coefficient DKA is equal to 2 by 3 into Rp 8 RT by pi m to the power of m of, that is equal to 2 by 3 into 10 power minus 6, 8 into 82.1 into 1.013 into 10 power 6. This we are going to use to convert atmospheres into the pascals, multiplied by 600 degree Kelvin divided by pi into 28, that is equal to 0.045 centimeter square per second. This is the dKa value. So this is the way one can estimate the dKa value. Once if you know the dKa value and if you know the partial pressure differences, then one can estimate the flux. And this is the one problem. This is another problem where I can read out the problem. A mixture of nitrogen and hydrogen diffuses at standard atmosphere and 293 degree Kelvin through a 25 millimeters of thickness unglazed porcelain membrane. Calculate the pore diameter of the solid. Right? What we are talking about, a mixture of nitrogen and hydrogen is there, which is diffusing at a standard atmosphere and 293 degree Kelvin through a 25 mm thick unglazed porcelain membrane, and we have to calculate the pore diameter of the solid. And here it is given as d of H2N2, diffusivity of hydrogen through nitrogen, is given as 74.3 into 10 power minus 6 meter square per second at 288 degree Kelvin and 1 standard atmosphere. We have TH2N2, that is effective diffusivity coefficient, is 5.3 into 10 power minus 6 meter square per second, the same values. And try to see the difference here. Actual the diffusion coefficient is 74.3, but the DAB effective diffusion coefficient is 5.3, which is almost 14 times lower than the actual diffusion coefficient. This is because we are using a gross surface area to calculate the actual diffusion coefficient, but in the real systems, when you are talking about the porous systems, we cannot use the gross surface area and we have to use the actual surface area, and it is not possible to calculate the actual surface area. However, we are estimating diffusion coefficients. That is the reason the actual diffusion coefficients are maybe 14 times lower than this value when you talk about this system. And we have dKH2 effective, that is diffusion coefficient of hydrogen, Knudsen diffusion coefficients of hydrogen, which is the effective value, is 11.7 into 10 power minus 6 meter square per second at the same temperature and the same pressure. Now, as we discussed, DAB by DAB is equal to constant, that is also equal to dKa dKa by dKa effective. This is what we have discussed in the previous time. So where DAB value is given, DAB effective value is given, and that is going to become constant, and that is also equal to dKa by dKe effective. So from this, what one can do, dKa can be calculated. Before calculating this is going to become DAB by DAB effective multiplied by dKa effective, that is equal to 74.3 into 10 power minus 6 divided by 5.3 into 10 power minus 6 into 11.7 into 10 power minus 6. That is going to become 16.4020 into 10 power minus 5 meter square per second. And your D pore radius is equal to pore diameter is equal to 3 into dk hydrogen pi mH2 divided by 8 gc RT to the power of 0.5. That is nothing but 3 into 16.4020 into 10 power minus 5 into pi into 2.02 divided by 8 into 1 into 8314 into 293 to the power of 0.5, that is equal to 0.28 micrometers. Then the last thing which is left out is hydrodynamic flow of gases. And if the pore sizes are very, very big, and then the diffusion will not take place, a convective flow is going to take place. The pore sizes are very big, the diffusion is not going to take place. What do you call it? A convection flow is going to take place, and we can also tell about whether the flow is a laminar flow, whether the flow is a turbulent flow. If the Reynolds number is less than 2100, one can say it is a laminar flow. If the Reynolds number is more than 2100, one can say it is a turbulent flow. And this can be estimated is equal to, that is hydrodynamic flow, d square gc by 32 mu L RT into PT average into PT1 PT2. So this is the equation that we are going to use for the estimations of flux if the flow is the hydrodynamic flow, where no simple diffusion is taking place. The convective flow is going to take place. It is nothing but a flow of fluid through the tube, a flow of fluid through the tubes. The pore sizes are very, very big, and there is no diffusion is going to take place, and the flow is taking place as if the pores are very big and as if it is a straight tube that we have. So where d is the diameter of the pore and mu is the viscosity, L is the pore length, and R is the universal gas constant, T is the temperature, and PT average is the difference in the pressures, PT1 minus PT2, where PT average is PT1 minus PT2 divided by 2. And once if you have this expression of flux, and one can calculate the flux, and during this derivation one can assume that there are no end effects. This is what we are talking about. This is the pore. Generally we are going to come across the end effects. We are neglecting the end effects. So we are assuming that the flow is of a laminar flow, the flow is not of a turbulent flow, because still we are assuming that the Reynolds number is of the fluid is around less than 2100. So the fluid flow is taking place by laminar flow, end effects are neglected. So once if we are going to assume all these things, we can get Na is equal to this, and by using this expression one can calculate the flux value. So this is what diffusion through the solids, and diffusion through the solids we are going to come across at several places, as I told you, and there the flow may be taking place in a steady state fashion, maybe the flow is taking place in the unsteady state fashion, and even in the case of a steady state fashion, maybe the flow is taking place through the non-porous barriers, or maybe it is taking place through the porous barriers. If it is a non-porous barriers, what we said is, we said whether it is a polymeric membrane, whether it is a crystalline polymers. If it is a polymeric membrane, we have absorption and diffusion is taking place. If it is a crystalline polymers, so there are 5 mechanisms that we have discussed. Is the interstitial mechanism, interstitiality mechanism, vacancy mechanism, crowd ion mechanism, diffusion along the grain boundaries. So when you are talking about diffusion through the porous media, maybe the pore sizes are reasonable pore sizes we have, then diffusion is taking place because of the concentration difference, and there is no hydrodynamic flow is going to come into the picture. When you talk about the diffusion through the porous membrane, and the diffusion is going to depend what is the value of D and what is the value of lambda. If D by lambda is greater than 20, the bulk flow is going to take place, bulk diffusion is going to take place. If the D by lambda is less than 0.2, then Knudsen diffusion is going going to take place. If the d by lambda is in between 20 and 0.2, then both Knudsen diffusion and the bulk diffusion is going to be important. And we are estimating, it is not so easy to estimate the actual surface area where the mass transfer is taking place. What we are going to take, we are going to take the gross surface area. Because we are taking the gross surface area, the actual diffusion diffusivity values are very low compared to the actual diffusion coefficient values. So that is the reason we said effective diffusion coefficient. And fortunately, for a given solute and a polymer system, AB by DAB effective is constant. Once if you have estimated that value, it will be a constant for at other conditions also. You can use the same value for the finding out the DAB effective value. Once if you know the DAB effective value, we can calculate the flux. So similarly for the Knudsen diffusion, then when you talk about the hydrodynamic flow, it is the pore sizes are very big. It is it is nothing but a diffusion of the material through the porous media. It is diffusion of the material through a pipe, where pipe is having some radius and other things. So we can use the equation which is similar to the Eigenpoisson equation, what we have used, what you have derived in the moment and transfer class. So we can use a similar sort of equation for the estimations of the flux, and in this case, if everything is known, one can estimate the fluxes value. So this is what I want to conclude it, and this is what we are completed the diffusion through the solids. So what I will do is, in the next class, I will give you a lot of problems as assignment problems, and once if you look at those assignment problems, and if you can do that homework, and you will get a lot of confidence on this values and other things, I mean confidence on this chapter. Okay, thank you very much.